I'm Kevin. Welcome to my cave. Over on my little series about what I keep in my parts box, I mentioned that I no longer stock Zener diodes. The reason is that for me, an IC voltage reference does everything that I used to use a Zener for, and generally does it better. I promised you a video to explain how these are used, partly because these things are like racehorses, while Zener diodes are more like plow horses. The IC references need more care and feeding to get their peak performance. These ICs generally use the same schematic symbol as the Zener diode, except that it has an extra terminal, the reference pin. The reference pin is used to program the Zener voltage. You program it by hooking it to a voltage divider between the anode and cathode pins. The apparent Zener voltage will be the reciprocal of the divider ratio times a reference voltage given in the device datasheet. Usually, the manufacturers make the reference voltage 1.25 or 2.5 volts. By choosing the divider resistors, a high voltage part like the TL431 can be set to a voltage anywhere from 2.5 to 36 volts. What's inside the device that accomplishes this trick is a fairly simple little circuit with an op-amp, a transistor, and a circuit called a bandgap voltage reference. In this video, I'm not going to delve deeply into the voltage reference. It's a really clever circuit invented by the legendary analog designer Bob Weidler. But I haven't gotten nearly far enough along in the series on transistor theory to explain how it works. But given power on the larger device's cathode and anode pins, it outputs a reference voltage that is remarkably stable with temperature and the cathode-anode voltage. Let's show it in a typical Zener diode configuration. We'll put in the voltage divider outside the chip and hook it to a power supply through a current-limiting resistor. We'll start by remembering the two rules for an ideal op-amp. The input's drawing no current. Sure, that's helpful. But at first glance, it looks as if we don't have negative feedback, because when we look at the circuit, there's nothing but a constant voltage reference connected to the inverting input of the op-amp. But this is one of the odd cases where we get negative feedback through the non-inverting input. If the voltage on the ref pin rises above the reference voltage, then the op-amp's output voltage, which is the transistor's base voltage, will also rise. That will make the transistor pass more current. And the increased current draw will pull down the voltage at the cathode terminal and at the middle of the voltage divider. Obviously, deviations in the opposite direction will propagate the same way. Since any deviation of the ref pin away from the reference voltage causes the op-amp to make a change that pushes the ref pin back in the right direction, we do indeed have negative feedback. So the voltage at the ref pin will equal the internal voltage reference of the chip, and the only way for that to happen is for the voltage across the divider to be the reference voltage times the reciprocal of the divider ratio. And that's the equation we started with. Oh, one more little point. To make these references even more like Zener diodes, manufacturers often include on the chip a diode pointing in the reverse direction, so that it will also do what a Zener does when it sees a reverse voltage. You have no idea how mind-boggling this was the first time I saw it. The device powers itself from the voltage it's regulating. There's no other power supply. It's entirely floating, so it can go anywhere in the circuit. It can regulate a voltage of either polarity. If you want to tie the cathode to ground and regulate a negative voltage at the anode, it just works. It's like a universal Zener diode, only without the problems of current and temperature dependency, and with a lot lower noise. All in a part that in late 2024 is less than a quarter in quantity 10, or a dime a piece if you're buying them by the reel. But don't take my word for it. Let's build a test circuit and show that it works. I'll use a TL431 reference, which is a so-called high-voltage part, meaning that it's designed to work with conventional 24 or 30-volt op-amp supplies. Some newer references are limited to 6 volts or even 2.5 volts. Other parts in the same series are TLV431 and TLHV431, which are lower voltage and lower power parts. They're great parts, but not the same. The TL432 and its siblings are the same part with a different pinout. Another Jellybean series for this sort of application is the LM385. They're also cheap and popular. I just happen to have TL431 on hand, so I'll continue discussing it. TL431 has a 2.5 volt reference voltage. I want a voltage source with a 7.5 volt output, and I want to be able to pull 20 milliamps off it. Much more than that, and we're looking at a power supply, not a voltage reference. Usually voltage references are just going to the inputs of op-amps, so sometimes they need only to source microamps. I'd like the 7.5 volts to be correct to within 1% or so. I think that's the requirements for now. Let's fire up the CAD system. Future Kevin here. I realize that the time it took me to draw the circuit neatly is way too long to put in this video, so I'm going to fast forward over it and occasionally pause for comments. I'll set up the drawing with today's date and call it a TL431 demonstration circuit. I'll put in the input power and ground connections and mark them with power flags so the KiCad rules checker won't scold me. This will be a conventional Zener diode regulator, so it needs an input resistor to limit current. I'll fill in component values later. Now for the adjustable Zener, connected to power and ground. We'll put in a voltage divider to the reference pin, as we just saw. And I'll document the properties of the output. TL431 is sensitive to how much capacitance it's driving. It can drive a very low or very high capacitance load. There are a set of curves in the datasheet to explain what the boundaries are. I won't get into that here, because when I look at them, I see that 10 microfarads is always enough, so I'll just add that and not bother with figuring it out. For the sake of the demo, I'm going to want to measure both output voltage and current, so I'll show on the schematic where the meters go. And I'm going to need some sort of demonstration load. What I plan to do is put in a bank of dip switches that will drive LEDs at various levels of current so that I can step through a whole range. Toggling the load will result in a rapid transition, so I'll add a bypass cap close to the switches just as a matter of good practice. The LEDs need their dropping resistors. And of course, I'll draw the LEDs themselves. And I'll wire everything in. Now for the resistor values. I'll guess a 1.6 volt forward drop for a red LED, and set the currents to 10, 5, 2, 2, and 1 milliamp. Now for the rest of the resistors. The op-amp inside the TL431, like any real part, isn't an ideal op-amp. The datasheet says that the ref input can draw up to about 4 microamps. For the precision I want that to be less than about 0.5% of the current in the divider, so that I can ignore it. We need at least 800 microamps in the divider, and the lower divider resistor will drop 2.5 volts. So it needs to be at most 3.1K. I'll go with a standard value about half that, 1.8K. I can live with 1.4 milliamps through the divider. The top resistor will drop 5 volts, so 3.6K is right for that. Finally, we need to size the current limiting resistor. The load will draw up to 20 milliamps. The TL431 itself, according to the datasheet, will draw 0.6 milliamps. The voltage divider will draw 1.4 milliamps. That's a total of 22 milliamps. 4.5 volts, the amount that the resistor will drop, divided by 22 milliamps, is 204 ohms, so a 200 ohm resistor will be about right. That looks pretty good. The electrical rules checker finds that I somehow managed to create no connection symbols down in the title block. I have no idea what happened, but things are fine when I delete them. Now to the breadboard. Once again, I'm doing everything in time-lapse. You don't need to see my fumbly fingers in real time. I'm going to use the upper power rail on the breadboard for the 7.5 volts. So I'll put 12 volts into a column on the left side and run the series resistor up to the rail. I'll add the upper resistor of the voltage divider and the TL431. Then the lower resistor goes to ground. The anode of the 431 gets grounded, and the cathode goes to the 7.5 volt rail. The 10 microfarad bypass capacitor goes in between the power rails. This is enough to test whether the circuit is regulating with no load. So I'll stick in a couple of test wires and hook up a couple of multimeters. When I hit the power, I see 7.414 volts, a little over 1% low. I didn't quite meet the 1% target, but I wasn't all that likely to with 1% resistors. I'll talk at the end about getting better precision. But right now it's time to test how the circuit performs under load. I'll lay the bank of dip switches here to sort of plan the layout. I'll put in the 0.1 microfarad bypass cap and run the 7.5 volts to the bottom side of the switches, including a bunch of short jumpers so that the 5 rightmost switches are all connected. And I'll place wires out to the right that will be going to the LEDs. In go the dropping resistors. And the LEDs themselves. The cathodes of the LEDs all go to ground. Time to hook up the multimeters again and test it for real. I'm stepping through the currents here and recording what the nominal 7.5 volt line reads. When I plot the result, I see the output voltage drooping a little bit with respect to the current draw. And that pulls it even farther off the 1% goal. But when I look back at the schematic, I see a boneheaded move. I put the voltmeter on the load side of the milliamp meter. On the 200 milliamp range, my milliamp meter uses a 1 ohm shunt, so all I'm seeing is the resistance of the meter, plus about 1/10 of an ohm for the test leads and such. No surprises there. Let me connect the voltmeter to the line side and try again. Better record what I'm doing. Break the voltmeter connection, make some room at the right, and make the voltmeter connection to the 7.5 volt rail. Advance the revision, save the file, and it's off to the breadboard to make the modification. With the meters connected correctly, I'll grab a few sample data points. I don't think I need all the 21 current values that I provided for. Plotting that out, the droop is replaced with a little bit of climb. The voltage is still off. I could just decide to accept that, but one reason I want a clean, stable voltage reference is for VCO control voltages, and those are sensitive. A 1% error is something that a musician will hear as being out of tune. So let's take a quick look at the sources of error. I'll start by measuring the voltage on the reference input. 2.48 volts. Almost 0.8% low. I'll need to keep an eye on that. What's the voltage on the 7.5 volt rail? 7.41 volts. That's saying the divider ratio is about 0.4% off, in the same direction. Those two between them account for the 1.2% or so that we're seeing. And now we know that the reference voltage is varying with the output current, because the divider ratio isn't going to change. A few quick tests at other currents confirm that. We saw in our graph that the effect of changing the current is pretty minimal. But the TL431BC I'm using is supposed to be a 0.5% part. Why is the reference voltage so far off? TI has an application note about this that I'm linking down in the doobly-doo. It shows how to adjust the parameters for a given voltage and current that the reference has to deliver. TI states in the datasheet for the part that I'm using that the reference voltage is expected to drop as the cathode to anode voltage increases. They give a typical figure of 1.4 millivolts per volt and a worst case of 2.7 millivolts per volt, where the voltage in the denominator is the output voltage minus the 2.5 volt reference voltage. The reference is actually a nominal 2.495 volts, says the datasheet. 2.495 volts minus 1.4 millivolts per volt times the 5 volt or so offset, 2.488 volts. Okay, that's part of the explanation. If we use the worst case 2.7 millivolts per volt rate, 2.481 volts, dead on what we're seeing. And the 2.495 volts isn't an exact figure. The datasheet shows that even under nominal conditions, the starting voltage could be in the range 2.483 to 2.507 volts. I think there's nothing for it but to trim out the offset. I might be able to hold everything in spec by using 0.1% resistors and accounting for the voltage dependence. But for a hobby project, it's not worth bothering. If I were designing a circuit for production, I'd have to worry about the labor cost of adjusting the trim, and so I'd have to put more effort into a no-tune design. I'll put a 100 ohm trim pot here and try again. Advance the revision once more. Off camera, I installed the pot and trimmed it. Now let's see how we're doing. No load, 7.5 volts straight up. A little under 5 milliamps, 7.502 volts. A little under 10 milliamps, 7.503 volts. About 14 milliamps, 7.504 volts. About 19 milliamps, 7.505 volts. Now it's better than 0.1%. I'll take it. For a production circuit, I'd have to analyze things like manufacturing variability and thermal stability, but this is good enough for a one-of-a-kind. We've seen here how we can use a bandgap reference to get quite a precise voltage source, good enough for stable musical tuning. Trying to do that with Zener diodes would be a fool's errand. There's a whole zoo of additional clever things you can do with these parts. The TL431 datasheet has circuits for using it as a comparator, as the reference for a higher power but precise power supply, as a precision current source, as a thermometer, and a bunch of other things. You may see one or two of them in later episodes. And that's why I don't keep Zener diodes in my kit very much anymore. I hope you enjoyed getting into this fairly deep dive into managing bandgap reference ICs. Next time, I'll be back to our regular series, exploring transistor behavior and op-amp circuits. I hope you'll stay tuned for that, and even subscribe so you don't miss an episode. Until then, stay safe, stay healthy, stay curious, and take care of one another. Bye!